Having seen that systems possess a kind of electromagnetic inertia and how a changing magnetic flux through a wire loop can induce a current in that loop, and having described this effect with the qualitative relationship known as Lenz's law, we're now ready to modify Kirchhoff's voltage law, uh, KVL or the loop law, to account for the possibility of a changing magnetic flux through a loop. This is going to be called Faraday's law of induction. And doing so, we will arrive at a new kind of electric field that behaves in new and different ways from what we're used to. An induced electric field that has looping E field lines that do not begin and end on electric charges, and an induced electric field that does path dependent work, non conservative work, a non conservative form of electric field. This phenomenon is known as electromagnetic induction. And it's the heaviest set of concepts we have in this semester. But it's also the most wonderful and the most fascinating electromagnetic induction. Okay, let's start by making these modifications to our existing laws to try and account for the effect we've seen of changing magnetic fluxes. So starting with our potential field relationship along some open path. So if we start at point 1 and move to point 2, traveling along this path, the change in electric potential along that path we know is equal to the opposite of the open path integral of E dot ds along that path. So if there is a potential difference between these 2 points, there must be electric field in the region between those 2 points. Okay, that's what we know. But now we're considering the possibility that there is a magnetic field in this region as well, and moreover, that magnetic field is a function of time. And if that B field is changing in time, that's going to change this equation. It's going to add an additional term, what we'll call the Faraday term, due to the presence of a time-dependent magnetic field. I can't write down the exact expression for this term right now because it requires some math that's beyond the scope of our course. But we can write down an exact expression here if instead of considering an open path from here to there, we consider a closed path instead that loops around and returns back to where it started. And in that case, we might consider this potential field relationship along a closed path. We might really consider that to be what we've been calling Kirchhoff's voltage law. If we have a closed path, a closed loop, then starting here, let's say at this dot and traveling this direction around, then the delta V along that path, well, if we return all the way back to where we started, the delta V should be 0. We end at the same potential at which we started. So that's the opposite of the closed path integral of E dot ds around that path. So in the past, or up until now, this right-hand side would always have been 0. If you integrate E dot ds around some closed path, you'll find that E does some maybe positive work for a while, but then negative work and 0 net work overall if you go around some closed path, so that it agrees with you returning to the same potential. So no overall gain or loss in energy if you return back to where you started. However, if now we have some magnetic field in this region as well, some external magnetic field that is a function of time, then this Faraday term that I suggested up here can have an exact expression. This is the expression for that Faraday term. If there is a time-dependent magnetic field, then there's a time-dependent magnetic flux through the open surface bounded by our loop. And that time-dependent magnetic flux appears in our equation in this form. We have the opposite of the time rate of change, the first derivative with respect to time, of our magnetic flux. That magnetic flux, as we've defined earlier, through our open surface here bounded by our closed loop is given by this integral, the b dot dA. Here's all our little dA vectors pointing out of the page for all the little patches of surface area on our open surface. B dot dA through that open surface. If this flux is changing with time, then we need to account for that in this equation here. So let's consider what this is implying. Okay, I've kind of redrawn that picture here of a region of magnetic field in a closed loop, little ds displacement vectors tangent to that loop, showing that we're integrating, in this case, counterclockwise around that loop. I have little dA surface area vectors pointing out of the page. Okay, this was our delta V term, which was 0 if we start and end at the same point. And then here's our Faraday term that we've added over here. So, okay, just rearranging this, I'm going to move the minus E dot ds over to the left-hand side here and express what we're now going to call Faraday's law of electromagnetic induction. What this is saying is that if there is a non-constant magnetic flux through your a non-constant magnetic flux through the open surface bounded by your closed loop, then there will be an induced electric field in this region with a non-zero integral around that loop. Note how weird this is. This is saying that if this flux is changing, if the flux through this surface is changing, then there will and must be some electric field in this region, even if there are no electric charges around to create that electric field. Up until now, we've seen that electric fields were only ever produced by positive or negative charges, and all our field lines begin and end on charges. This equation is now saying that there will be E field here, even if there are no Q's around to create it. If the magnetic flux is changing, an E field, an induced E field, will appear in this region. So we'll be doing a lot more thinking about this induced E field and what it looks like and what its properties are. Let me note a key aspect of utilizing Faraday's law successfully has to do with this negative sign right here and its interpretation, its meaning. Why do we need that right there? It really comes from Lenz's law. It comes from our need to our need to represent that electromagnetic inertia that we see exists in these systems. This minus sign here is really all important for guaranteeing that this induced E field has that corrective inertia-like effect. Okay, so what do you need to know about utilizing your this negative sign and signs in general with this equation? So note, if you're using Faraday's law and you're doing this closed path integral around some loop, the direction of your ds vectors around that loop, the direction of integration, clockwise or counterclockwise, that direction must agree with the direction of your little dA surface area vectors perpendicular to your open surface. In other words, your choice of a front face for your bounded open surface. You get to choose a front side and your back side, but that choice is not totally free. The direction of ds and the direction of dA have to agree with each other according to the right-hand rule. So here's another application of right-hand rule. Let me explain. Look at these two pictures here. If we're going to choose this path and integrate in a counterclockwise way around it, so our ds's point tangent to the path kind of counterclockwise, then take your right hand, curl your fingers in the direction of the ds's, and your thumb points in the direction that you must choose for dA. dA must be out of the page if your ds's are counterclockwise. That's in order to get all the signs to agree here in Faraday's law. If you accidentally put dA into the page here, then you'll get a sign disagreement in the equation. So what if instead we just decide to integrate clockwise instead around some path? You absolutely can. You can integrate either direction you want. So we can make our ds's clockwise instead. But in that case, we still have to get this agreement here. So if you're going to integrate clockwise, then take your right hand, curl your fingers in the direction of the DS's, and your thumb, pointing into the page, points in the direction that DA must point. So if you're going to integrate clockwise, then we'd be looking at the back side of the open surface, and our DAs would be pointing into the page. Here, if we're integrating counterclockwise, then we're looking at the front side of our open surface, and our DAs point out of the page. That's key for getting these signs to work out and for Lenz's law to be represented accurately in this relationship. Okay. So we're about to move on to discuss these two properties here of this new kind of electric field, this induced electric field. That's coming up next. We'll end this video on a quick note that looking back at the past, when we studied capacitors, the farad, capital F, the SI unit for capacitance, that's named in honor of Michael Faraday, the English scientist for whom this law of induction is named.